Okay, class, welcome to lecture 19. So today we are talking about functions. And this is something that you've seen before. You've definitely seen the word function before a long time ago, but you've never properly studied them until this class. So we're going to go through it, see what they are, and learn about properties and then prove stuff about them, like always. Okay, so the first thing is that we want to think about, functions before I define it, just the intuition. We want to think about functions as like a process or just a way, processes that turn sets into other sets. So really a function is just something that turns one set into another set. I'll put this in quotes because I haven't defined it yet, but in like a very specific way, not in any way you could possibly imagine. Okay, so let's actually define it then. So what is a function? A function is something that goes between two sets. So in the definition, I need to have two sets. So given two sets, A and B. Of course, these can be very fancy things, but right now they're just arbitrary sets. Given two sets, A and B. A function, it's a directional thing. So it's got to go from one to the other. So we'll just say it goes from A to B. What is a function really? It's a rule for turning things in A into things in B. And this is how you say it in a very mathy way. It's a rule that assigns to each element. So I'm going to use little a to represent just any old element of A because I don't actually know what the set looks like. So it's a rule that takes little a's, any element you want, and assigns to it, or you can think about it as sending it somewhere, assigns to it exactly one element of B. And that element of B you write as, well, actually, I'll name it later. One element of B. So the idea is that every single guy in A, every single element in A, has to go somewhere in B, has to get assigned to something in B, but you can think of it as like a directional thing, like it gets sent over to B. And it has to be done in a very specific way. Everything, that's the word each is saying here, every element in A has to go somewhere, has to get sent to something in B. And you can't send each thing to multiple places. So that's what this is saying. If you have an element of A, it can only go to one thing in B. It can't go to two different places at the same time. That's what a function is. It's a rule that does this, that accomplishes this goal. So we have notation for all this that makes it a little bit easier, though, and this is the notation you're more familiar with. So if we name a function, so a very good function name is f. So we name the function f. So f is the rule that turns little a's into things in B. So once you name the rule, then we can write things like this. Then we write that f colon a arrow b to mean the function goes from A to B. So this is indicating that f goes from A, so it's a very directional thing, to B. And then if you want to say where these little a's go, what we do is we call them f of A. So this means the element that A goes to. That the unique element that the A that you're starting with is assigned to. So that's all the notational stuff. And then just to be extra clear, this is not really part of the definition, but the idea is A is an A, and then this thing that you call f of A, which is where A gets sent under the function f, that's got to live in B, because it's an element of A getting sent to an element of B. So very often we can visualize functions, and that's what we'll do later, and it'll help us understand more, because it seems like a very big definition right now. But it's really just a rule that turns elements of one set into elements of another in a way where everyone goes somewhere and nobody goes to two different places. Okay, so let's look at examples. Oh, actually, there's some more terminology. So one more bit of terminology. We call A the domain and B the codomain. Of course, that just depends on what letter you stick here. This is always the domain, whatever's on the left, and whatever's on the right is always the codomain. In this case, A is the domain and B is the codomain. Okay, of F each time of F. Usually you don't have to specify because you've already known what the function is called ahead of time, so you wouldn't need to worry about it unless you were dealing with multiple functions. Okay, so now I'll do an example to hopefully make this a little clearer. So for an example, what do I need? Well, I need two sets because a function has to go between two sets in the first place. So here's my two sets. A's got x, y, and z. B has 7 and 15. And I'm going to just define a function. And this is way different than the way you're used to defining functions a long time ago, where you just say something like f of x equals x squared plus 3x plus 2, stuff like that. But what we do here is we actually say where every element goes. So we define a function that goes from A to B by just writing down each assignment. So aka where each element of A is sent to by using this notation. So f of, so I don't have to start, I'll just start in the middle. F of y, I have to send it somewhere. F of y has to be something in B, and it's where y is getting sent to. So why don't I send it to 7? Because that's something in B. I also got to say where x goes. I'll send that to 15. And then I also got to say where z goes. So I'll send that to 15 too. So this defines the function f because I've said where every single element of A should go. X should go to 15, Y should go to 7, and Z should go to 15. And no element goes to two different places, meaning X only goes to 15. It doesn't go to 15 and 7 or something. Y only goes to 7, it doesn't go to 7 and 15. And Z only goes to 15. So those are the two defining properties of a function. And I've created a rule that follows both of those properties. So let me just write that right here. For any A in A, f of A is just a single element in B. That's what I should say unique. That's the better word. So each A is getting assigned to a single B. So A could be X, Y, or Z, and B could be 7 or 15. Each A only goes to one of 7 or 15. Okay, so a really helpful tool is doing something to help you visualize what's going on. So that's what we'll introduce next. So we can visualize functions by drawing our sets sort of as these like blobs. It's not a very technical term, as blobs. So here, this will be A, this will be B, and then this is not a very like technical thing, so you can sort of change it up however you want, but what I'm going to do here is I'm going to draw dots and label each dot as the elements of the set. So those are the same two sets I'm dealing with up here. A is x, y, z, B is 7 and 5. And then the function, to indicate the function, I'm just going to draw the assignment. So where did x go? Ugh, my memory's horrible. X went to 15, so I'll draw an arrow from x to 15. Where did y go? It went to 7, so I'll draw an arrow from y to 7. And z went to 15 as well, so I will draw an arrow from z to 15. And then these arrows indicate the definition of the function f. So this helps us visualize a function. And so now we can think about these two properties sort of in terms of these arrows, and it's a little bit maybe easier to visualize this property. So to be a function means that elements in A, they all have to go somewhere. So is that true? Yes, all 3 dots go somewhere. And you can't send one dot to 2 different places. So each dot only has 1 arrow coming out. And so if you could just look at the picture and see that, then that's enough to say for sure it's a function. Okay, so let's do a non-example. Those are always just as good as examples. So consider the rule. So I'm not calling it a function because it's not going to be a function. It's just going to be a rule that goes from A to B. I'll use the same A and B as before. And here's what the rule will do. So I'll send x to 7. I'll send x to 15. I'll send y to 7. And I'll send z to 15. So this is not a function because x is getting sent to 2 different places. And I can visually see that this is bad very quickly if I just draw a picture of this rule. So this time I won't include dots. I'll just literally put the letters as the dots themselves. That's fine too. So this is saying that G sends x to 7 and x to 15. That's the bad part already. The other stuff actually is fine. Y can go to 7 and Z can go to 15. So the fact that x has 2 arrows coming out is what disqualifies it from being a function. Okay, but you can also just say, oh, x is getting sent to 2 different places, so it's not a function. All right, so this does not happen for f, as we saw in the picture. Okay, so let's do another non-example. So consider, I'll use another name, the rule h from A to B, defined by, so very often when people make rules, they write the definition of the rule underneath the function notation there, so I'll do that this time. So I'll send x to 7, and I'll send y to 15. So same as before, same sets as before. So why is this not a function? It's because I didn't say where everything in A goes. Didn't assign Z to anything in B. So that's why this rule is not a function either. Visually, we can see that too, just by the fact that what's wrong with this picture is that Z has no arrow coming out. So you got to have every element going somewhere to be a function. And this doesn't have that property, so it's not a function for a different reason than last time. Okay, so those are the 2 disqualifying factors of being a function. So let's just draw a whole bunch of examples and see what's going on. So this time I won't even label the elements, I'll just put dots. And you could put your favorite labels, whatever you want your elements to be called. So this is a function, sort of like the best possible case, actually. I'll think about that next lecture. What about this one? So this guy, is it a function or not a function? It is a function. So you might be thinking, but what about this thing? This element has no arrows going into it, but that's okay. That doesn't need to happen for it to be a function. All I need is that both of these guys go somewhere. They do. And neither of them go to two different places. And they each only have one arrow coming out. So yeah, this is a function. You can have extra bits over here on the right, and that's okay. Still counts as a function. You don't have to hit all the dots on the right. Okay, so something like this. Oops. Something like this. So this guy, is it a function or is it not a function? No, for two reasons. It's bad twice. First of all, every element in the domain does not go somewhere because of that guy. And second of all, this guy goes to two different places. So this is not a function for two different reasons. What else? Let's see. I think that covers all the possibilities that I can think of. So this one is a function. We'll even add an extra dot here. So everyone likes to go to this element on the right for some reason, and so nobody's going here, but that's okay. Okay, so visually speaking, that's the difference between functions and non-functions. In terms of arrows, so it's sort of much easier to see when something is a function if you draw it like that. Okay, so next, now let me remind you of what you did learn about functions a long time ago. So the functions you learned about in like those old classes like calculus and pre-calculus, those are functions of the form, mostly, not always, but mostly. They were functions that would take in real numbers and spit out real numbers. And you wouldn't literally write down something like, okay, 3 goes here, 2 goes here, 1 goes here, because you would never be able to write down every possible thing. So that's not what you did, like what we just did up there, where we said where each element goes. Instead, when you're dealing with numbers, you can create a rule by just assigning where a variable goes. So for these, we create functions or rules by saying where an arbitrary element goes. So we might do something like f goes from R to R, defined by, I'm just going to say where an arbitrary element goes. I guess I'll call it x, and it's going to go to here. So that tells me where every element goes, because if I want to know where 10 goes, I can just use this rule, 3 times 10, so that goes to 30. So that way I don't have to manually say where every single element goes. So that works when you're dealing with numbers and you just want to do operations between the numbers to create rules. Whereas when you have elements like we were talking about before, which are just like random letters or numbers, and you can't combine them with operations between numbers, then you just sort of have to manually say where everything goes. But usually the sets are small enough to be able to do that. Okay, and then very commonly, so this is the common way to do this. So they'll either do something like this. They'll say, okay, the function name is f, and I'll write the rule just right underneath it. So maybe like x squared. Or this other one I like better. It's cooler because it's new and fresh, and you haven't seen it before. Instead of doing this, you just say, you draw a little arrow with a line in front of it, and you say like x is going to go to, I don't know, 2x plus 10. And that just means g of x is defined by 2x plus 10. Just a different notation for the same thing. So you could also do that with the left one here. So I could have said x goes to x squared. You don't have to use both. You can use either one, but it's just another cool little notation. Okay, so just to summarize, if your function is going between sets where you just list out all the elements, then you pretty much have to just say where everything goes manually. But if your function is going between numbers, sets of numbers, then you can probably use a rule to make the function. Okay, so more fancy terms. That's what I've labeled this next section. Fancy terms. Let's spell better. Fancy terms. Okay, so we'll just jump right into it. The image of a function f, also called the range, but I like to call it the function, the image better. So the image of a function f, so I guess I already know that it goes from a to b. The image of a function f from a to b, written as, so I'm going to write it as im of f is the set of elements in B. So the idea is the image is all the stuff in B that actually gets hit. Because as we've seen from pictures before, just very quickly, you can have a function where not everything gets hit by the function. So this guy is not being hit. Why can't I change colors? Oh, because it broke. Good. Come on. Okay. Ah, what is this crap? What the heck is wrong with this app? Sorry, everybody. Okay. Oh, it just didn't save what I just did. Good. All right. Perfect. Not at all frustrating. The image of f, written as imf, is the set of elements in B. So what I'm trying to say is that they're the ones that actually get hit. Smaller example to save time. So we've seen that something like this is allowed to be a function, and so you have something in the codomain that doesn't even get hit by the function. So nothing you plug in goes to that guy. Nothing gets assigned to it. So the image of f is the set of elements in B that do get hit. Which you have to say in a better way, and I will in a second, but I like to say it this way too, that are hit by the function. So that, of course, is not a real definition. So I have to say the real thing. Formally, how do I say the list of stuff that actually gets hit by the function? Well, it's not so bad. So it's just a set. It's a set living where? Where do the elements come from? Well, they come from B because it's going to be stuff in B in the second set, in the codomain. It's going to be stuff over there, but not the whole thing always, right? Because we can have leftover stuff like the stuff in this, like the dot in this red square. So it's not all the stuff. It's just the stuff that equals the function evaluated or plugged in for an element of A. So this is exactly saying the more intuitive idea, which is it's the stuff that actually gets hit by the function. So it's the elements in B, not all of them, just the ones that look like f of something. Okay. So then as a quick note, the image of f is automatically a subset of B because all of its elements are coming from B. They're just the ones that actually get hit by the function. So B could be bigger than the image, or it could be the whole thing. Okay, so just a quick little example. So here's a new A and a new B. So the letter X might be confusing because I used it in the definition, but it could be a different letter. Okay, so here's the rule. I gotta make a rule to think about. So I'll use this notation. F of 1 is gonna go to X, F of 2 is gonna go to Y, and F of 3 is gonna be Y as well. So visually, 1, 2, and 3, X, Y, and Z. 1 is getting sent to X, 2 is getting sent to Y, 3 is also getting sent to Y. So then, the image of F we can get just by looking at it. So it's just the elements that actually get hit by the function, so just X and Y. Z is not in the image because nothing goes to it. But then to be very formal about it, it's because X equals F of 1 and Y equals F of 2. Now, Y equals F of 3 as well, but it doesn't matter if it gets hit twice. It just matters if it gets hit once. So you could say because of that or because of Y equaling F of 3. Either one is enough to tell you that it's in the range, that Y is in the range, because they're both telling you that Y gets hit. You only need one way though, you don't need both. Okay, so meanwhile, Z is not in the image because Z does not equal F of A for any A. There's just no A that you can plug in. You can't plug in 1, 2, or 3 to get you to Z using this function, so Z is not in the image. I shouldn't use the word for any, actually. Let me just say no matter what. Okay. So now we're going to jump back to functions between number sets again. So let's do that. So in our domain and codomain are sets like n, the natural numbers, or the integers, or the rational numbers, or R. We define functions usually just using operations. And then finding the image is a little harder because I can't just like look at a little picture that tells me everything that gets hit or doesn't get hit. Okay, so let's think about some examples. So let's define f from z to z. So I'm sure you've never done a function like this before. By f of 2 will be n plus 2. And again, I could just write, sorry, I have to say where n goes, not 2. And I can also say that n gets sent to n plus 2. You don't have to say them both. I'm just getting you to practice both notations. So now, what is the image like? What actually gets hit? So we'll eventually talk more about how to think about this. But for now, we're going to be very hand-wavy. The image of f, well, you're just asking what integers can I get? And so one way to think about it is just call any integer m. Can I create m by plugging something in? What would I have to plug in to get m? Well, because the function does whatever you plug in plus 2, if I want m to pop out, that means I need to plug in m minus 2. So what this is saying is that the image is actually all of the codomain, because any integer you can possibly imagine, 100, a million, negative 37, if I want it to pop out, if I want to hit it, how do I hit it? I hit it by plugging in that number minus 2, and that'll get me that number. So figuring out the image here is a little bit trickier than it is in the previous problems. And it can change a lot depending on the sets you use. So let's see what happens there. So I can keep the function the same, but I'll make the domain be the natural numbers instead. So now the image of f, well, the lowest number I could plug in is 0, and that's going to get sent to 2. So really, I'm just going to get the numbers 2, 3, 4, and so on like that. And that's because f of 0 gets me 2, f of 1 gets me 3, and that's how the pattern continues. And I'll never be able to get the numbers below 2, because I can only plug in natural numbers now instead. Okay, so there's just little mini examples of finding the image. Now, let's think of another fancier example of a function. So we just learned about products of sets. So in fact, I can define functions out of or into products or between products. So haven't done that yet. Sorry, I was just scrolling up for a second. Okay, haven't done that yet. Okay. So how does this work? Well, to create a function, I just have to say where elements go. So what are elements of this set? Well, they are ordered pairs. So I have to say where an ordered pair goes. Now, very technically speaking, that means you actually need a second parentheses. But I'm very often not going to do that, so I might as well just give up right now and not have that second parentheses. Unfortunate math notation, but this is what people write. Okay, so I can define a function from z cross r to r which means I have to plug in an integer and a real number. And then on the output, which is sometimes what people call what comes out of a function, I'll just do something like, I don't know, m plus x. So this is a perfectly reasonable function. You can think about the image if you want. I'm just trying to introduce more interesting functions. You could also have functions that go from a product to another product. So that means you have to say, I'll use different letters, but it doesn't really matter. You have to say where. You have to say what happens in two different coordinates. So maybe you do n plus y here and n minus y there or something. So that defines another function. So you have to say what you're getting in the second set. And because the second set now also consists of ordered pairs, you sort of have to make two different rules, one for each coordinate. Okay. So I think that's all I want to talk about for today. So we didn't do any proofs, so hopefully this is a slightly easier section. But proofs will be coming next time when we actually study functions in general. Right now, what we're doing is we're sort of just studying examples of functions and just seeing different types of things that could happen. But next time, we will have kinds of functions with specific properties to study. And with that always comes proofs whenever you have properties to talk about. Okay, so see you next time.